During the 1950s, the Australian government, in conjunction with state governments, began a program of geological mapping of the entire Australian continent at 1:1 to 250,000 scale, which equates to about 1 inch equals 4 miles. The mapping was accomplished doing field traverses and was accompanied by geologists using aerial photographs. The maps produced during this program have underpinned the discovery of many of the mines operating today. During the 1970s, following completion of the broad-scale mapping, a program of more detailed mapping was undertaken in mineralised terrains or in areas of more complex geology. By the late 1980s, the regional geophysical data sets, mostly collected by airborne surveys, in other words, surveys carried out from aeroplanes, helped to refine the earlier mapping. Geophysical data sets include aeromagnetics and radiometrics, ground gravity surveys. These data sets were compiled at mapping scales and underpinned many of the advances in the maps. This slide shows radiometrics on the left, which is a measure of the relative amounts of uranium, thorium and potassium in the rocks, and represents a good proxy for rock type. The magnetics on the right that shows the magnetic characteristics of the rocks. The next slide shows the results of the map that come from those particular using those particular data sets. So you can see the sorts of complexity of geological information that we can derive from airborne surveys. However, the true value of geophysical data sets lie in their capabilities to allow mapping of known geology under cover. Many of the newer discoveries in Australia over the last 10 years have come from using geophysics to define blind targets. Aeromagnetics allow us to trace faults under cover. This particular map covers several hundreds of kilometres from north to south. The black area there defines the outcrop area, and you can see how we can use aeromagnetic images there to extend the geology from the known to the unknown. These slides also can show us areas where we can trace magnetic characteristics from areas where we know what they are into areas that are undercover. So this becomes very important when exploring undercover. Recently, geophysical techniques such as magnetotellurics, airborne electromagnetics and deep seismic profiling have been used to add a third depth dimension to our knowledge of the geology. This has allowed us to construct 3D models, particularly in data-rich areas. We are also using detailed geochronology programs based largely around a super high resolution microprobe, which we can use to date zircons. This data can be constructed into time-space plots, which allow us to understand the relative timing of geological events and allow us to construct more robust tectonic models. Here are two time-space plots from different parts of Queensland. While not all surface discoveries have been made, it is broadly agreed that the next generation of discoveries in Australia will be made on blind targets up to several hundred metres of cover rocks. In order to allow effective exploration under cover, a good understanding of the mineralising system is required. If we're looking for elephants, we look in elephant country. Once again, there's not a lot of point in looking for elephants in Kazakhstan. But if we look at this particular slide, it can show us that unless we have some idea of what we're looking for, we can be very, very easily misled into thinking we're seeing something different. So we now start to use a mineral systems approach to the discovery of deposits rather than just simply trying to identify geophysical targets of what we hope is known mineralisation. The mineral systems approach uses the answers to 5 questions What is the geodynamic setting of the system, the architecture of the system, what are the fluids, their sources and reservoirs, what are the fluid flow drivers, and what are the metal transport and deposition processes. You will note that these questions relate from the regional scale in the first question down to the much smaller scale for the later questions. At the regional scale, the continental geodynamic setting influences what type of mineral deposit we should be looking for. I will now illustrate some of these questions, how they're used in the assessment of mineral deposits in the Mount Isa Inlier in Australia. Mount Isa is one of the most heavily mineralised terrains on Earth, with several world-class deposits, including the Mount Isa lead-zinc deposit, Mount Isa copper, Century zinc mine, Ernest Henry copper-gold mine, and the Cannington lead-silver mine. I will look at mineralisation in the Inlier using 3 deposit styles to illustrate how answering the 5 questions can assist in exploring for new deposits. The 3 deposit styles are shale-hosted lead-zinc, shale-hosted copper, and granite-related copper. This is a diagram of a shale-hosted lead-zinc system. These systems occur in shale and carbonate-filled graben structures. The fluids are derived from salt-rich beds drawn down deeper into the basin during continental extension. We can see the carbonate, the salt beds around about the seawater sediment interface there. The fluids then liberate lead and zinc from feldspars in sandstone beds deep within the basin. The fluids are then expelled during compression following cessation of the extension and migrate up along the faults which mark the edge of the basins. These deposits are either deposited either on the seafloor or in highly reducing black shale layers. So these systems are therefore entirely constrained within the upper crustal part of the sedimentary basins, within the top few kilometres of the crust. Looking for new deposits relies on the identification of these basins and possibly these events which drive the fluids from deep in the basin to shallower parts, and also in the location of early formed bounding faults. Now, this is a rather complex figure. I'm not really trying to get you to understand all of this. When we start to look for shale-hosted copper deposits, and we must realise that at Mount Isa, the shale-hosted copper and the shale-hosted lead-zinc occur both in the same mine, but there is quite a big contrast in terms of the source for the copper, because we generally find that the copper is derived from deep crustal or possibly upper mantle sources, often in multiple stages. This slide shows the multiple stages, so that the copper is derived from the brown and pink areas down right at the bottom of the slide, and the slide shows different mechanisms for getting that copper up into the top of the crust. So the models for the generation of sediment-hosted copper require a mechanism to get fluids and copper from deep in the crust into the upper crustal settings, where the copper, like lead-zinc, is deposited in black shale beds. In order to achieve this, deep crustal faults are required in order to tap the deep crustal fluids. Expelling the fluids occurs during major regional compression events which affect the whole of the crust. So we're not just looking at local basins as we were for the lead-zinc system, but much larger scale orogenesis is required. So in order to find new shale-hosted copper deposits, we would need to identify these very deep, very major crustal faults, and we can also look in terms of the timing of mineralisation to occur during very large regional compression events. So it's a very different system to the rather local system, and we're using different exploration techniques in order to explore. The third system I would look at are granite-hosted copper-gold. Like the shale-hosted copper, these deposits need to transport fluids and copper and gold from deep in the crust to much shallower environments. However, the mechanism for transport is different. In this case, the fluids accompany granite intrusion rather than requiring deep crustal faults. So in order to find new granite-related hot copper gold, we need to understand which granites are implicated in driving these deep fluids up into the upper part of the crust. The figure shows the copper deposits identified in the Mount Isa inlier. The deposits over on the west are aligned very strongly along faults, and these are the deep crustal faults that we can identify both from geophysics and from our geological mapping. The deposits in the east show a much more scattergun approach, and these are the deposits where we find the copper gold associated with granites. So to put this in the context, the techniques that we require to find new deposits under cover, we look for what sort of data we would need to identify possibly mineralised regions. In the case of the shale-hosted lead zinc, we need to identify the presence of extensional basins, which require salt-rich layers. We also need to identify graben-bounding faults. Such basins can be identified during regional geological mapping by observing thickness changes in sedimentary sequences, with changes in thickness required to occur across graben-bounding faults. We can use geophysics, mostly magnetics, to trace these faults under cover. So we can use the things like magnetics and airborne electromagnetics to identify fertile shale basins. We also need to understand the sedimentary and geodynamic environment. Many of these inversion events are reflected in the change in the sediments that we find in the basin. So sandstone beds in a shale basin would indicate a change in geodynamics and may represent periods of inversion. So in searching for shale-hosted copper, we need to identify deep crustal faults, and such faults are often associated with changes in crustal structure and can be mapped on aeromagnetics and gravity profiles. An understanding of the basin evolution and the timing of major orogenesis is critical to identifying prospective areas. All of this preceding discussion highlights several important points. Reliable geological maps are the basis for understanding the geology and are the prime requirement for finding future mineral deposits of all types. In order to effectively target deposits, particularly under cover, we need to understand the type of deposit we are looking for. We need to understand the mineral system in order to know what features are critical for the localisation of the deposit. We need to immediately find the deposit. We perhaps can identify the fluid pathways, which can then provide us with a vector to where the ore itself is. And particularly if we are targeting deposits under cover, we need to acquire the appropriate geophysical data, particularly regional data sets. Now finally, the development of these models has taken place under a close working relationship in Australia between government, academia and the mining and exploration industry. Over the last 10 years, I've been involved as a researcher in a cooperative research centre, or CRC, where the 5 questions model was developed. Cooperative research centres are projects with well-defined structures, timeframes, outcomes, which are funded by contributions from government, academia and industry. Sometimes the contributions are in kind, where academia provide researchers as their contributions to the CRC. This model has the strength of targeted research, which is of value in the industry and in which in many cases can be supervised by the industry, and which is therefore more likely to be adopted by industry in their exploration programs. However, the attention to the needs of industry or programs may not be developed exploration strategies, much to the value of the research is lost. Thank you.